Okay, welcome back, you lazy bums. So we're going to throw some lectures back at you guys after a brief hiatus. Running some experiments there on you guys, unbeknownst to you. But anyways, come right back at you. Going Unit 6B, because we did kind of cut that last unit short so that I could try to maybe piece some stuff in before the finals, but I didn't want to be beholden to that. So here we go, Unit 6B. The objectives with this particular lecture: first of all, we want to be able to correctly draw Bohr diagrams for various elements. You were introduced to those today on the ChemQuest. And then also to be able to use Bohr diagrams and the periodic table to predict trends in atomic radius. And the kind of the theme here with Unit 6B is to really start looking for trends and patterns on the periodic table dealing with the arrangement of electrons. All right? These are two objectives. So first and foremost, Bohr diagrams are models of atoms, and we use them to show the number of electrons at each energy level. So, for example, boron. If you were to write the electron configuration for boron, you would do so by going S2, right? So boron has 5 electrons, right? So we're going to put the first in 1s, and then we're going to go 2s2, 2p1 is the way that would look. So again, 1s2, 2s2, 2p1. All right? And so how that translates to a Bohr diagram is you'll see that we have energy level 1 occupied and energy level 2 occupied. So that's the 2 rings. So this is the ones that correspond with energy level 1. This is the ring that corresponds to energy level 2. Now, notice energy level 1 has only the s sublevel. We can only put 2 electrons there. So that's those 2 dots that we see there. All right. Energy level 2 for boron can hold up to 10 electrons because we could put, up to 8 electrons, excuse me. We can put 2 in the S sublevel and up to 6 in that P sublevel. But boron only has 1 electron in that P sublevel. So we have the 2 plus 1, 3 electrons. So notice with the Bohr diagrams, we're just putting circles or rings for the energy level, and we're not worried about the orbitals or the sublevels in this case. Those do tell us how many electrons we can put there, but we're not showing those with the Bohr diagram. Now carbon, very similar to boron, right? So its electron configuration is 1s2, 2s2, 2p2, right? So there's those 2 electrons here and here from energy level 1, and then those 4 electrons are shown 1, 2, 3, 4, and then likewise with nitrogen, we're 1s2, 2s2, 2p3. So we should have 5. 1, 2, 3, 4, 5. That outer ring. Okay? So each ring corresponds to an energy level, which is the number, those coefficients that we're putting in there before the sublevel, and then the number of electrons or dots we put on that ring is determined by how many electrons are in that outer energy level. So one thing you may notice then is to decide how many rings or how many energy levels you need to show in a Bohr diagram, it's just simply what row the elements are in. So boron, carbon, and nitrogen are in the 2nd row, so we would know to automatically start with our nucleus and just go 1, 2 rings, right? If I was doing aluminum, for example, which is in row 3, I would draw a 3rd ring around that, all right? And then figuring out how many electrons to draw is determined by essentially how many electrons are in that energy level, right? You can kind of count that from left to right. It's fairly simple. All right. So, whoops, wrong way there. So we're going to draw some Bohr diagrams for some other elements. So we'll do sodium. Sodium has 11 electrons, right? And it's in the 3rd row. So I'm going to draw my dot for my nucleus. So in the 3rd row, so I'm going to go row 1, row 2, and then row 3. All right. So I know that energy level 1 can only hold 2 electrons. 1, 2. Energy level 2 can hold up to 8 electrons. So I'm going to add 1, 2, 3, 4, 5, 6, 7, and 8. So that gets me up to 10 electrons total. Sodium atomic number is 11, right? And so I have one more electron to add. So that makes 10, so that 11th electron goes in that last energy level. We're just going to C1. All right. Now, if I was to write the electron configuration for sodium, or even the abbreviated one, I'd go like this: Ne3S1, right? And so there's that one electron in the third energy level right there. That's our guy. All right. Now moving ahead to magnesium, right? Its atomic number is 12. So I would draw it just like sodium. It's in row 3. So there's my dot, row 1, row 2, row 3, and of course you guys can probably draw better circles than I do, right? I got 1, 2, and then 8 more. There's 10, 11, 12, just like that, okay? And that would correspond to Ne3S2, and there's those 2 electrons. So that is Bohr diagrams. All right, so essentially, again, you look at what row we're in. That tells you how many circles to draw. You fill all the inner circles with up to 8, and then whatever's left over goes in that outer circle. Now, the next topic brought up on your Chem Quest was this idea of shielding. Okay, so looking at sodium, right? The nucleus of sodium has 11 protons, so the charge of the nucleus would be plus 11. Magnesium has 12 protons, so its charge would be plus 12. Okay, now what we have to do for this idea of shielding is we have to then consider how much of that charge works its way to the outer electrons. Okay, so if we go back and look at sodium, for example. Sodium has 11 protons, right? That charge of plus 11 from the nucleus gets blocked by the electrons on the energy level. So we want to know how much of that charge actually makes it all the way out to that outer electron. Okay? And so what you have to remember is electrons have an equal but opposite charge to protons. So each electron will remove one charge from the nucleus. Okay? So sodium has a plus 11 charge. It gets blocked by 10 electrons before it gets to the outer electron. So the charge felt, right, the charge that actually reaches the outermost energy level is a plus 1, right? Because 10 electrons on those energy levels block 10 of that charge. So we're left over with plus 1. Now magnesium, likewise, which has a charge of plus 12 at the nucleus, again, 10 of that charge gets blocked by those inner electrons, making only a plus 2 reaching the outer electrons, okay? And those inner electrons that block that charge, that's what that shielding is called. And that's what they were referring to on your Chem Quest, right? So we have a total charge of the nucleus, but each electron that's present blocks one of those charges. And whatever makes it to the outer ring there is unshielded. Whatever gets blocked is shielded. All right, so if we draw Bohr diagrams for potassium, right? So potassium's in row 4. Calcium is also in row 4. So what I want you to do right now is to pause this YouTube video, pause it, and I want you to go ahead and try to draw Bohr diagrams for both potassium and calcium. All right, give that a whirl, right? And then hit play again, and you can see how I drew them to see if they correspond. So please pause, take a moment, draw those Bohr diagrams, and then come back and see if you did it right. Did you pause it? Did you pause it? Oh well. Anyway, so potassium has 19 electrons total. It's in row 4. So again, I know I'm going to go a dot for my nucleus, and then now I'm going to draw 4 rings. 1, 2, 3, and 4. Okay, so energy level 1 gets 2 electrons. Energy level 2 gets 8. Energy level 3, now it can hold up to 18 electrons, right? Now, I don't have 18 electrons left over, so why am I worried about that 4th energy level? Okay, this takes us back to the fact that energy level 3, the S and P gets filled, then it jumps up to energy level 4, then it goes back down to the 3D, all right? So what you have to remember is The energy level is only going to get 8 electrons before it jumps up and then back down. Okay, so that's why I'm telling you, if you just look at the row you're in, right? Row 2, row 3, row 4, that tells you how many energy levels to put in. So we're only going to put 8 in an energy level before we jump up, right? We may have to jump back down later, right, for some of the more complex BOHR diagrams, but that's one of those things you're just going to have to remember and try to relate to what you learned in the previous unit. All right. So again, potassium, there's 19 electrons total, right? Because of my atomic number is 19. There's 2, there's 8 more, there's 10. I can put 8 more to make 18. 4, 5, 6, 7, 8. That's 18. I have 1 left over. I'm going to have 1 electron in that outer ring. And calcium, very similar. It's got 20, so I'm just going to add 1 electron to what I did for potassium. So it's in row 4. So there's my nucleus. Row 1, row 2, row 3, row 4. I'm going to go 2. There's 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. Okay? And that's how that should look. And notice that these guys end like this. This would be AR4S1, and this would be AR4S2. There's that 1 electron right there. Those 2 electrons are there and there. All right? So your outer ring gets 8 electrons because S and P gets filled, then the next energy level, and then it goes back down to D and so on. All right? That might be a little confusing. This will come together for you, I promise. All right. So how large is the charge felt by the outermost valence electrons in each of the above, right? So hopefully at this point, you guys recognize the pattern. If there's 1 electron in the outermost energy level, the charge felt on that is 1. If there's 2 electrons in the outermost energy level, the charge felt by those is 2. All right, and we can see that still based on shielding, but that's just a quicker way to look at it. But again, potassium has a charge of plus 19 at that nucleus, right? We got 2 plus 8 minus 10 plus minus 8 more. That's minus 18, so 19 minus 18 plus 1. There's that 1 charge that makes it all the way out, okay? So again, we have 18 electrons occupied in energy level 1, 2, and 3 before we get to 4s, right? So 20 minus 18 plus 2, right? 2 electrons, there's plus 2 charge felt by those 2 electrons. Right. Now, why does it matter how much charge is felt by those outermost electrons? Why are we putting a focus on that? All right. That has to do with our atomic radius. Okay. So there's 2 things that are going to affect how big your atom is, the radius from the nucleus to the outermost electrons. One of them is shielding, and the second thing is the number of energy levels, or the number of rings that we would draw on our BOHR diagram. All right. So the atomic radius decreases as you place more electrons in the outer energy level, okay? And so we see a corresponding decrease in the size of the atom, right, as you go from left to right. So let's say, all the elements in row 2. So we got lithium, and then we got beryllium, and then we've got boron, carbon, nitrogen, oxygen, fluorine, and neon, right? So that's left to right. So they all have 2 rings in them because they're all in the second row. But because there's more charge reaching that outer ring, right? So lithium, the charge reaching the outer ring is plus 1, plus 2, plus 3, plus 4, plus 5, plus 6, plus 7, and plus 8, right? That's how much charge reaches the outer level. The bigger that charge is, the closer or the stronger the pull on those electrons. So neon is feeling a plus 8 charge on its 8 outer electrons. And so a plus 8 charge is going to cause those electrons to get pulled closer into the nucleus. And so our radius, even though we have 2 rings, is going to decrease as you work your way over. Okay? So the radius decreases as you place more electrons in the outer energy level. And the trend we see there is as you move left to right, we're putting more and more electrons in that outer energy level, and so we see a corresponding decrease in the radius as a result, because the nucleus has a stronger pull on those outer electrons. All right? Now, the second thing that we need to notice is the effect of going down the periodic table. Okay? So the more rings I put on my atom, the larger my radius is going to be, right? And so as we go, like, let's say lithium, sodium, and potassium, for example, which are all in group 1, right? So lithium is only going to have 2 rings. Sodium is going to have 3 rings. Potassium is going to have 4 rings. 1, 2, 3, 4, right? So as we go down the periodic table, our radius increases. Okay? So the trend on the periodic table, because of shielding and the number of energy levels, is that as we go left to right, we get a small radius. As we go down, we get bigger. Okay? So that means that, in theory, our biggest atom would be at the bottom left, which in this case is francium. Right? So in theory, based on what we're seeing right here, francium at the bottom left of your periodic table should have the biggest radius. Okay? So again, we get bigger as we go down and bigger as you go left, or you can think of it as smaller as you go up and smaller to the right. So therefore, our smallest atom, in theory, would be helium, which is at the top right. All right, that's it. Hopefully that clarifies some of the stuff you guys worked on the Chem Quest today. We will hit that some more tomorrow as we proceed, and then start talking about things like electronegativity and so on. Peace.